There we go. So welcome back. Happy Tuesday. Happy garbage day. Lovely fall day. I've got the syllabus up in front of me because I sent out an email yesterday letting you know that you have some new things to do. So next thing due is formative assessment number 4. Has a different format. It's multiple choice. So it's about changes in variance upon adding different types of fixed effects. So this is one in which there is a correct answer, and so you'll get to see correct answers after you turn it in and the due date passes, but we're still going to go over it like normal so we can talk about the reasoning behind why things go up, down, or stay the same. After that, the next week, the day before Halloween, homework 3 is due. That one is, as I mentioned in the email, a little more complex than usual, so I would recommend starting on the early side. Just a hint. But of course, office hours back to normal as well. Nikki just told us, as I just fixed the website a second ago, she's back in her old office in 440 Lindquist Center on the north side. So hooray for that. Other things that are happening with respect to the syllabus, just a heads up that next Thursday, a week from Thursday, we're back on Zoom. We are having comprehensive exams in this room and we are being kicked out. So, such is life. All right, so I don't have the stuff ready for Thursday yet. I was working on that, but in terms of the schedule compression that I saw, I decided to ditch one of the examples that I had planned, which is a crossed model for subjects and items, because that is what chapter 12 of my book is all about. And that has accompanying materials on the book's website, in SAS and in Stata. For that one, I did this example in a workshop a couple years ago, I guess more than a couple years ago at this point. Speaking of time flying, so I have resources from that as well. So on Thursday, we'll talk about crossed models using regular general multi-level models, meaning conditionally normal outcomes. And then we switch gears a bit next week into the generalized unit. So generalized models are when you're predicting some kind of outcome that is not normal. So binary, ordinal, nominal, counts, things that are bounded at 0, that kind of thing. I have a whole class on that. It's coming back in the spring. If you haven't had that class or you haven't had coursework in logistic regression or count regression, those kinds of things, I would highly recommend reviewing the generalized modeling course. You, in the very first lecture, I think, in the introduction to this class, I listed specific examples and lectures that would be helpful to review. I am going to go over it, but it will go better if you're hearing it for the second time rather than the first. But the good news is that everything you learned about generalized models from before and everything that you learned about multi-level still holds. It's just putting it all together at the same time. So we'll have that, and then that ties into a particular type of measurement model called an explanatory item response model. And you don't need to know what that means in order to follow this, because this is essentially a demonstration of how to use crossed random effects with generalized models at the same time. And after that, we'll see what we have time for. It's like potpourri, right? So your last homework will be something generalized. I'll have to decide which one I want to do. So I know that we will have covered that by the end of the class, for sure. Your homework 4 materials are not yet available. I was waiting to see how many people were doing papers and what kinds of papers they were going to be doing so that I could develop a rubric for it and release that. So my plan is to release either the rubric for homework 4 if you're doing analysis of cluster data on your own, or your actual assignment if you chose the AI option by next week, so that you have a couple weeks to work on that as well. Sound good? Yay! Yay, school! Mm-hmm. I know this is the point in the semester where we're all starting to get a little tired. I feel it too. We can hang in there though, we can make it. I know that we can. So any questions on that? No? Zoomers, you with me? Thumb check.
Yes.
Yes, excellent. Voice check too, however you want to participate, it's all good. All right, then I will shut this down. And where I thought would be useful is to go back to example 4. We started that a week ago. Maybe we could re-go over it. Would that be helpful?
Yeah, not re-going over.
Yeah, re-go over. We'll do it. So as I mentioned last time, this is one of the few data sets in which it is actually real data. So the data set that goes with this example is not available online. I lied, data are not there. But complete syntax and output are available in all three of the programs. So we have about 13,802 students from 94 schools. We are predicting end of 10th grade math outcomes from really a single variable. Like conceptually, all we're looking at is the extent to which an ordinal representation of free lunch status, where 0 means they pay full price, 1 means they have reduced price lunch, and 2 means they receive free lunch, to what extent that relates to student math outcomes. But because these students are nested in clusters, it's going to be more complicated than that. Yeah, it's like understatement of the year, right? Wait till you see where I end up by page 20. It's going to be amazing. So in terms of data processing, the ordinal variable that I'm working with, I am eventually going to be representing by two different slopes here. For the first half of the example, I'm just working with this one because binary is something that I wanted to emphasize. This variable represents the difference between students who pay full price and students who get some kind of discount. So if I just dichotomize this variable, that's what I would get. However, eventually, adding to the story will be a variable that distinguishes the latter two categories. So this method of coding is equivalent to your standard dummy coding, but it does change the interpretation. If this variable is all that's in the model, then it's the difference between paid as one group and reduced and free lumped together. Once I add the second variable, this one changes to become the difference between paid and reduced specifically, and then this one picks up the remaining difference between reduced and free. So this type of coding, sequential coding is what it's sometimes called, I think is useful for ordinal variables because it gives you the direct differences between categories rather than comparing each one back up to a single reference. The good news is that you can do it either way. So if you have three groups, you need two slopes. How you make them, how you distinguish the groups is completely up to you. It's an interpretation decision, not a math decision per se, because you can always get all three possible pairwise differences regardless of your coding scheme. So we set that up. Just in terms of descriptive statistics, 70% of the kids have full price lunch, only 8% get reduced, and the remaining 22 get free. So this breakdown is at the student level. I created cluster means, this is stated code to start with, for each of the dummy coded predictors, as well as a set of indicator variables just for straight ones and zeros for each group so that I can check the means to look at the distribution across schools. Here's where we did that for the cluster means. And then in Stata, this option, preserve collapse, that is being used to maintain the original level 1 data set, but temporarily reduce it to a cluster level data set so that we can run descriptive statistics. Then you can go back using the command restore to the original student level data set so that you can make other new centered predictors. So doing that, this summary here, this is from SAS, but it looks the same in any package. We have the proportion of students who get each type of lunch on average. So 70% is the school mean in terms of the proportion of students in a school who pay for lunch on average, and it's 0.11 for the proportion who have reduced lunch and 0.19 for the proportion who have free. So these numbers I'm using to create like a representative school based on the centering for these cluster mean variables of my slopes. So I picked 0.3 as a centering point for the first one that distinguishes paid lunch versus reduced or free, so that I would have a representative school that has 30% people who get reduced or free. For the second one, that distinguishes paid or reduced from free, that one I centered at 0.19, so that putting it all together, the reference school has a profile that looks like this. So the reference school's profile matches the proportions in the original data on average with respect to lunch composition. So this gets tricky, right, Vladimir? We figured this out the hard way. He was working on a problem that had a whole bunch of these binary predictors. And it's very easy to create a situation in which you have an impossible school because all of these proportions have to sum to 1. So paying attention to where your constants are to create your representative school is an important thing if you're trying to make predictions after the fact to talk about what effects would look like for typical children in typical schools and that kind of thing. Okay. Does that part make sense in terms of the building of the things? So order of operations, make your dummy codes first. So make these variables first. Then take the school means of those, then center the school means at a representative proportion with respect to how many students have each category on average. Same thing in R, all the usual codes here. I am creating first the new dummy coded variables to distinguish the groups, then the indicator variables to make sure I know what I'm doing, using Jonathan's function for add unit means to get means for all of these variables, and then asking for them to be described, so descriptive statistics, and then doing the cluster means centered at a constant, and then creating within cluster versions, because I'm eventually going to need those to test random slopes. Okay. Any questions before we dive back in? Well timed. No, we're good? Good enough? Zoomers, we good? Am I here? Am I hallucinating that I'm teaching right now? I'm not asleep, right? Okay, there's all the thumbs, right? This is not just a really vivid dream, because I do have those. I do end up teaching in my dreams. And sometimes it gives me ideas, and I like wake up and write down, oh, that was a good idea. I should try that. Anywho, so we're predicting math. First step, always an empty model. So this is not a pedagogical exercise. This is useful in figuring out how much of your variability is at each level so that you can start to anticipate what role the predictors will have. The Zoomers report, it's hard to find the thumbs up. Yeah, I think if you like use it on a regular basis, it puts it first, but if you don't, then it doesn't. But you can pick whatever emoji you'd like. It's fine. So empty model here. How many parameters are in this model? Do a little review. How many things are we trying to estimate? How many fixed effects? We'll break it down.
1.
What is it?
The fixed intercept.
Yeah, that guy right there. That's the fixed intercept. That's the mean of the school means. That turns out to be 47. What are the other 2 parameters? And yes, these are observed math scores. What are the other 2 parameters? I'll give you a hint. They're in bold.
The variance component.
Yeah, these guys. So we have this one. That's my random intercept variance. So it's the variance across clusters in the U0 random intercepts. So U0C is for a school. It's the idea that each school needs their own, which in terms of estimation becomes the variance across schools. That number is 45. And what am I leaving out? One more. Yeah, there you go. So EPC is the residual for student P in cluster C. The variance across people and clusters is 253. In terms of dependency, if I form an interclass correlation, that's the 45 divided by 45 plus 253. That number works out to be 0.15. So what does that tell me?
A lot more variation within them between.
That's true.
So that is the proportion of variance due to school mean differences in that?
Nailed it. Proportion of variance due to school mean differences. Yep. So 15% or 0.15 is a proportion. So only 15% is due to school. 85% is due to kids. In a clustered data set, though, that's kind of high, actually. They tend to be smaller interclass correlations. In longitudinal data, I've seen ICCs up to 0.9. So, yeah. There's a lot more dependency if you survey the same person repeatedly than if you survey the same unit in terms of like a school or a cluster or an organization. That tends to
Lisa,
be the
I
case.
have a quick
Yeah.
question.
Go for it.
The standard error for I think it was the between variance.
Mhm.
So 7.15, that's on a standardized metric, right?
Unstandardized metric, yes.
Oh, that's unstandardized, okay, never mind.
Yep. Yeah,
was gonna say,
Stata
that's
does
pretty
that
high.
and it builds a confidence interval, but the interval, I believe, is asymmetric. They do something to it to make sure that it doesn't go past 0. Because for very small variances, that could happen. I'd have to check the manual to remember exactly what that does, but I typically don't worry about the confidence intervals or the standard errors for that matter, other than to make sure that they're not like 8 million. If you get a standard error that's way, way, way big, that indicates some kind of problem with your estimation. So they should be like reasonably sized, like in proportion.
If we did want to interpret that number, would that one standard deviation is equal to 7.15 in whatever metric the scores are in? That is,
No. So
no.
if you want to talk about like the differences across schools, then it would be the square root of 45 as the standard deviation.
Okay,
The standard error describes how precise the 45 is as an estimate of school mean differences.
okay, that makes sense.
Yeah, so like if I repeated this study in 10th grade classroom, or 10th grade grades, I'm out of words, 10th grade grades all across the country, then I could expect that this 45, that 7 is how far off from the mean, like that variance estimate would be in any one school. So it conveys the imprecision of the 45 as an estimate of the variance.
Okay, thank you.
Yep, easy to confuse those things. But yes, I did do a confidence interval, I'm pretty sure. Yeah, here's the formula for ICC. I did a design effect and I did a confidence interval. So to describe the expected variability in the school means for math outcomes, the center of it is always the fixed effect that goes with the term you're trying to describe, so that's my fixed intercept, plus 1.96 if you're using a 95% confidence interval and you're ignoring sample size, so that's a z, not a t. A square root of 45 then gives you the standard deviation for the differences across schools, and so here's the interval that I computed. So this describes, I think, in a maybe a more intuitive way, what the model is saying, how variable schools are in their mean math scores. Even though it's only 15%, it looks like a pretty big range to me. Humongous design effect of 22, given how many students are in a classroom and the relatively high inter-class correlation. So not nearly as much power as you would think, even though we have 13,000 students, works out to be power comparable to about 600.
Is that like bad?
Yes, like, I mean, 600 to me is still like a really big sample,
Right,
and to some folks that's tiny, but in my world that's very big.
right.
But you can envision a situation, right? Like if you only start with 100 kids and your design effect takes you down to 20,
Yep.
that's bad.
Right.
Yeah. That's bad. All right, so with me so far. Okay, and I can do a model comparison, a likelihood ratio test, to determine whether or not that inter-class correlation is significantly greater than 0. That works out to saying, hey, what would happen if I took my random intercept variance out of the model? So this is the likelihood ratio test that Renova gives you in R. The test statistic is 1,860, which we're treating as a chi-square. So yeah, wildly significant. That same number is also available directly in the Stata output as well. All right, so then same thing with respect to the lunch predictor, but it's ordinal. So that means that we don't need a separately estimated residual variance, and it means that we have to change how this variable is being predicted. So since we're going to talk about that starting next week, that's all I really want to say at the moment. But we get a random intercept variance we do not get a residual variance. If you're using a logit link function, which is what we're using to make sure the categories stay within their boundaries, we can use 3.29 in place of that. And so that's how Stata computes an interclass correlation, I believe, and so does R. So there's that one, and that one's even higher. So 35% of the variation in free reduced lunch status has to do with which school you go to. So a lot more commonality in that relative to math. And likelihood ratio test, again, wildly significant. Okay, so here's my first predictor. This is binary. Most people would prefer to leave a binary predictor at level 1 in its original binary form. So your slope is telling you how the 1 group differs from the 0 group. Your intercept is for the 0 group. Nice and tidy. So that's what I did. So I have my variable called paid versus reduced or free. Remember, that's the one where it's 0, 1, 1 in the coding. So we're lumping together any kind of discount at the moment, which is how it usually tends to be treated, it seems like. So we're sticking that variable in, giving it a fixed slope here in Stata, doing the same thing in R, and here's the results from R. We have reduced each of the piles of variance. 40% of the random intercept variance has been explained by student free and reduced lunch, and 5% of the level 1 residual variance has been explained. If I go to the solution for the fixed effects, 50 is the expected math score for what kind of kid?
Those who pay for lunch.
Paid full price. And what happens if you get a discount of some kind? Yeah, this is a finger question.
9 points lower.
Yeah, like 9.5 or 9.4 points lower on average. However, what am I forgetting?
Isn't this,
This is the smushed effect.
because we didn't tease out,
This is the Trojan horse model. We did not tease out, what's the word for it? There's a couple different ways we can say it.
something at level 2.
Something at level 2. I'll take that. Contextual. What about the contextual?
We're assuming that the between school differences is the same as the within school difference, so we're losing the contextual effect.
Yes, we're assuming that the slope relating between school differences and lunch to math is the same as the slope relating within school differences and lunch to math. Another way of saying that is that there's no contextual effect, or that the difference between those is 0. So it doesn't matter what the composition of your school is. That's what we're assuming. So this is a level 1 student characteristic. It should not have explained level 2 random intercept variance. The only way that it can is the level 2 school differences that are embedded in this variable. The Trojan horse is the analogy I'm staying with here. So 5% of all the reasons why some students have better math outcomes than others is related to their free lunch status. Yeah, so it's 5% of the 85%. We have to keep that in mind. In the empty model, 85% of the variance in math was due to students at level 1. We've got 5% of that 85%. In the empty model, 15% of the differences in math were related to school mean differences. We have 40% of that 5% in this model, assuming no contextual effect. Another way to say that, minus 9.4 is what this model says the within school effect is and the between school effect, saying they're the same. So we fix it. So I am adding a contextual effect. How do I know that this is a contextual effect and not a between effect?
Because we are using the original level 1 predictor.
That's it. This original level 1 predictor is the 0-1 version. It still has all the level 2 school differences in it. Therefore, What the school mean variable is going to do is to become the contextual effect for the difference, the incremental effect of the school composition after controlling for student individual lunch status. Incremental, that's the key idea here, after controlling for. Contextual effect is the, what if I took my kid and moved them to a new school, how does their score change?
Lisa, I have a question.
Please.
So you said you center the level two variable, especially in this case, so that if you're making predictions, it can be reasonable in terms of the outputs you get. Does centering affect model estimation at all?
In this case, no.
Okay.
So this centering, is that what you're referring to? The minus 0.3?
Yeah, because my longitudinal data is similar to this,
Mhm.
and I was wondering if some of the I think my data set's difficult to manage because it's so large, and that's probably what the problem is.
Could be.
But I'm just wondering if there are ways to reduce, because centering shouldn't affect it.
So the question is like, would this cause estimation problems or other kinds of problems if I didn't center? And the answer in this case is no. What would happen in this model? So what I have, the output I think makes it a little bit clearer. What I have are 3 fixed effects here and no interactions. So each of my predictors is the main effect without being conditional on anything else being 0. The only thing that would change would be the intercept, because if you didn't center your cluster mean, the intercept would be for a school where there's no kids that get free lunch. And mine is for a school that has 30% kids that get free lunch. Where you can end up with estimation problems from not centering is a level 1 variable that you give a random slope to.
Okay, I'm not doing that, so.
You're not doing that.
No.
Yeah, that's probably just as well. Because what happens is then the random intercept becomes conditional on the 0 value of the predictor the random slope is for. And if that's in a weird place, it maybe can't find the intercept variance around it.
Yeah, okay.
I've seen that happen before. It's only happened that I've seen in very extreme cases, so people who are using cognitive aging data with 80-year-olds who forget to center, then if you put age in the model as a random slope, then the intercept is differences between newborns as estimated from senior citizens. The model's like, I can't do that, that's too hard. Fair, right? That seems like a big ask. But generally, if it's a level 2 predictor, you can pick whatever constant or leave it alone. The reason that I centered this is, to me, it's weird to think about the effect of being a student who gets free lunch or not in a school where none of the kids get free lunch. That's just weird. I don't think it's wrong, like mathematically, but I don't like it. So I'm going to fix that problem. And you know me, we're only on page 7. There's going to be some interactions showing up. So making sure that each variable has a 0 point that is useful, I think is useful to me.
Great, thank you.
You're welcome. Thanks for the questions. So, recapping. This is my level 2 mean that is going to unsmush my level 1 predictor. Because my level 1 predictor is in its original 0-1 form, it still has all of its cluster mean differences in it. That means when I add the cluster mean of this predictor, it's going to become the level 2 contextual effect. And if I want to get the between effect instead, I can ask for it by adding these 2 slopes together, which I did here in Stata using this LinCom. And I did the same thing in R using contest 1D, which is down here. So within plus contextual equals between. I also in Stata saved the results from this model because I'm going to be doing a likelihood ratio test against it. And I did not have to save it in R, but I will be using that function in just a second. Okay,
Question.
hit me.
So I was trying to do this yesterday for a neighborhoods variable on neighborhood racial composition. So like predominantly white neighborhoods versus everything else was 0-1. And when I was looking through the data browser, it made everything. I just want to make sure this was right. It made everything into like very similar numbers. Then like is that I don't know. I didn't know that was right. So like it would make everything either 0 if they were like predominantly
So you had a binary level 1 variable,
Yes,
and you made a cluster mean out of it,
yes.
and then you looked at that column in the data set, and it still only had zeros and ones?
No, it had, I guess it had fractions of it. Is that correct?
Yeah, everything, it should range from 0 to 1.
Okay, and there should only be like a certain number of fractions that could possibly be, because all the, okay, there was like 6,000 data points of level 1, and like, you know, there's huge row of zeros, and then it went to like 0.01680, like, that's normal?
Yeah,
Okay.
I mean, it depends on how your zeros and ones are distributed, but yeah, that can happen. Mhm. So if you had like maybe 5 people per cluster or something, then you would only have a limited set of possibilities, right? You could have 0, 0.2, 0.4, 0.6, 0.8, or 1. But as you get more and more people, then you have more and more possibilities as you divide. So I think you're okay. Yes, happy modeling.
Lisa?
Yeah.
Yes, I have 2 questions related to the parameters we have in our model right now.
Okay.
So in this case, that intercept, that would be the expected outcome for the students who pay full price in schools with 70% of students who pay full price.
Correct.
Okay. However, that slope at level 2, that's the comparison between these clusters entirely composed of the students who pay the full price versus a school composed of the students who don't pay for lunch.
Yes.
Okay, so we can do the same thing as before, dividing that coefficient by 10, for example, and say that's the unique effect of the school after controlling for the level 1 predictor, right?
Yes.
For every 10% of the students who don't pay for lunch.
Yep.
Okay.
Exactly right. So let's do that. We'll look at the coefficients. Okay, so now 50 is the expected math outcome for what kind of kid? Kid who pays full price still. And what kind of school do they go to?
School where, 30% are free and reduced.
Yeah, 30% free and reduced or 70% paid. You can say it either way. But what 1 means is some kind of discount. So in terms of the proportion of cases that get a 1, it's on average 0.3, which is why I centered it at that point. So now, the difference in the coefficients here, the previous model is minus 9.42. The current model is minus 9.17. Very close together, and this is what almost always happens when you have a lot more observations at level 1 than you have at level 2. The smushed effect is very close to what the within effect wants to be, but it's biased. So you see in the smushed model over here, it's more negative than it is here because there's a missing negative contextual effect that's pulling it. So the previous model is biased to too negative for the within effect because of the missing contextual effect. So same conclusion, the only difference is that now we're talking specifically about 2 students who go to the same type of school. Holding school composition constant at 70-30 as the split, what is the expected decline in math related to free lunch status? Minus 9.17. And then this coefficient, as Vladimir said, is a little weird. It seems huge because you have to remember what a unit is. All slopes are the change in y for 1 unit change in x. A unit, because this variable is a proportion that ranges from 0 to 1, a unit is comparing a school with no kids who get a discount to a school where everybody gets a discount. And there are a few schools like that in the sample, but I think it's more useful to divide by 10. So we take the decimal, move it over like that, and we can say for every additional 10% of children who get a discount, the school's average math goes down by 1.68. And you might ask yourself, well, why not just scale your variable like that in the first place? You could do that, but then it breaks the rules of within plus contextual equals between because they're not in the same units anymore. So that's why I don't do it. There.
I'm sorry, just, just so I understand, 16, when we leave it as 16.8, that is what?
That is the difference between a school that has a proportion of 0 and a school that has a proportion of 1. Because a 1 unit is all the range of the variable that's possible.
Right, right. So that I get. But
Okay.
so for each one of these kids, if we move the decimal point over, it's what?
Per
Everyone
10%.
is- Per 10%, it's 1.6 worse. If we leave it like this, how do we say that in a sentence?
16.8 is the difference between schools who have 0 for their proportion of free lunch students and 1 for their proportion of free lunch students.
Thank you.
Or 1.6 per 10%.
Yep, okay.
Yep. Yep, I think the latter might be more useful to talk about, but in terms of making the between plus contextual equal between, or nope, between minus within equals contextual, within plus contextual equals between, then, yeah. So, yeah, I'm closing my eyes again. You probably noticed that if you attended my talk on Saturday, I can't use my brain and my eyes at the same time. I have to close my eyes to get the words out that I want to say. It's like you have to cut down on the extra stimuli. So I'm not trying to hide from you. I just literally have to shut my visual field off so I can find the right words out of my brain. All right, so here's the between slope then that the model implies. The -9 plus the -16 is the -26. So in terms of variance explained, here's the R² from the first model that was smushed. So a model assuming that the within and between slopes of free lunch predicting math are the same did this well. Our new model relative to the empty baseline did this well, and then here's the difference. So the way that I would think about this is that in terms of the total reduction, 69% of the school level random intercept variance was explained by school level math as a between effect. 5% of the student level variation was explained by student within school effect, and the extra contribution that you get from moving from the smushed model to the unsmushed model is due to the contextual effect, the extra part that the level 1 predictor doesn't have. So this to me was shocking when I first saw this. 70% of the variance is due to just this one proxy for socioeconomic disadvantage. Not good. Okay. All right, other questions? So this model assumes that this disadvantage, this -9, is the same across schools. Do we have to assume that, or can we change the assumption? We can change it, right? We can do whatever we want. How are we going to change it?
Random slope.
Yeah, this is a fixed slope. We can add a random variance around it. However, it's not quite that simple. We have to change the variable that the random slope is being given to make sure that the random slope variance is not smushed. So I am using a within cluster version of this binary predictor in the random part of the model, even though I'm keeping the original binary version in the fixed part of the model. So that's why I have two different variables in the Stata code here. Original binary is a fixed effect, within cluster centered version as a random effect. Cough, cough, your next homework. And the changes also, in addition to this random slope in Stata, you need to tell it that you want to let the random intercepts and the random slopes be correlated for the same level 2 units. That's not a default, like it is in R. So that's why the code became more complicated. I added a separate beta 2 here for the cluster mean centered version of this level 1 predictor, and I gave it the random slope, whereas the original binary version maintains the fixed slope over here. However, despite the weirdness of them being attached to different things, it works out that they still work together. Because in this model, where am I going? Where do I, here we go. In this model, after controlling for this contextual effect, that coefficient, that minus 8.4, is the pure within slope. So the model doesn't care if it is creating a within effect using a cluster mean centered predictor or a not cluster mean centered after controlling for a contextual effect. You get to the same place. So for all intents and purposes, you can think of the random slope as applying to this predictor. It's just that we're making sure that the random slope is creating differences across schools in this school disadvantage and not anything related to school composition. All right, and yeah, I did both programs of output since we hadn't seen a random slope yet. So now the coefficient has changed a little bit. It was minus 9 something, now it's minus 8. That's because it changes what it means. This is now the average disadvantage across schools. Two new parameters in the model for the variance. The variance of those disadvantaged slopes is 14. The covariance of the random intercept with those disadvantaged slopes is minus 7. So 14 seems like a lot, right? Seems? I don't have a p-value here. How do I know if 14 is significantly different than 0?
Likelihood ratio test.
Likelihood ratio test. Can I use this one? Here's a hint. 3 degrees of freedom. How many degrees of freedom should there be? If I want to test just the two new things. 2, yeah. I don't do trick questions. I only throw softballs. Usually underhand. So yeah, I got 2 new things here. So this hypothesis test is referring to 3. It's referring to this entire set right here. That's what it's saying. This is your answer to someone says, can I just run a regression? No. P less than 0.000001. But it's also lumping in the intercept variance, which we already had. So to test the contribution of the 2 new things, we need specifically to store the estimates from this model and compare them using the LR test function against the previous model with just a fixed slope. So I kept all the fixed effects the same. I only added the random slope variance and the covariance with the intercept.
So this is sort of like a multivariable test when we're testing.
Yes, in likelihood land. Yes. Yeah, if I were testing 2 fixed slopes, I could do it that way instead. So likelihood ratio test statistic is 90, and p-value is 0 to several decimal places. And we talked about this last time, and if you watched the video I left for you on Thursday, anytime you add a variance that has a null hypothesis of 0 and the variance can't go past 0, technically speaking, you should be using a mixture chi-square distribution instead. That means that you're changing your critical value, for instance, for 2 degrees of freedom from 5.99 to 5.14. And if you're like, yeah, I don't care, with you. I don't have time to care about that. So if I ignore that problem, then this is just a little conservative. Okay, I can live with that. So here's the corresponding R code. Here's my within cluster variable inside the parentheses for the random part here. R automatically estimates correlations between the random effects at the same level, so you don't have to ask about that. Correlation is minus 0.5 in this case. The interpretation of the intercept variance is changed. It's conditional now. So this is specifically at the 0 value for the predictor that has the random slope. So that is at the average for the school, which is a little bit weird. But if you think about the range between 0 and 1, this is in the middle of that, whatever your school mean is. That's where the intercept is. Why does this matter? Let me pull up a picture real quick. Here's the one I want, this picture. If the lines are not parallel, then where your intercept is going to matter in terms of how different the schools are. So it's going to be 0 in the middle here as opposed to at the end or at the beginning. All right. So here's another thing we can do to talk about effect size. I don't think it makes sense to talk about pseudo R-square or any kind of R-square for a random slope. I might be in the minority in that, but I will die on that hill. Because all we've done is take our 2 variance model, and we've taken some out of the residual that is due to school differences. So we don't know why some schools have a larger disadvantage than other schools with respect to free lunch. We know that they do. Yes.
Is that when we have fixed residual variance at level 1, for example, in the case of generalized models, when we try to create this random slope partitioning the level 1 residual variance, which is a fixed value, how is that possible?
It is possible. It stays 3.29 though, no matter what.
And we are taking part of that to level 2, but
Yes,
the value is the same, right?
yes.
Oh, well.
The model changes scale in generalized land. So if, like, the total variance has to grow in order for it to make sense that there's still only 3.29 left over at level 1.
Okay.
Yeah, I'll more on that is coming, but that's the big picture of it.
Great, thank you.
So we're not explaining variance. We're repartitioning it into 2 different ways that schools differ from each other in their mean levels of math and in the extent of student disadvantage related to lunch. That's what we have. And if we compute a random effects confidence interval, so now the fixed effect in question is the slope. So minus 8.4 is the fixed slope for my level 1 predictor that has the random slope with it. 2 times the square root of the variance that goes with it, so that's right here. And that creates an interval like this. So 95% of my schools are expected to have a disadvantage for student free lunch, anywhere as big as minus 15, all the way up to minus 1, barely any disadvantage. So that's, it seems conceptually like that's a lot of variability. And I fixed the typos that I had, some copy and paste errors in this formula to compute slope reliability. And yes, you get to do this on your homework as well. So the ingredients that go into this are the slope variance and the numerator, residual variance right here, level 1 sample size, and so I'm doing the average of it as an approximation. And this var thing, that is the variance of the predictor that the random slope goes with. So in our case, the predictor the random slope goes with is the binary variable. So that's how I would compute the variance of it, the mean minus 1 minus the mean. All right. Now, I'm pretty sure we didn't talk about this yet. So we've ended the re-go over portion of the program. So logically speaking, what we have learned is that schools differ in their mean math and schools differ in the extent of their lunch disadvantage. We can now try to predict why it is that some schools have a larger disadvantage than others. And I'm going to use the only variable that's in the story right now to do that, this one right here. So cluster mean of this variable, this is now forming what is known as an intra-variable interaction. This is asking if the extent of the disadvantage in your school depends on school composition of free lunch. Is it worse to be poor if there's fewer poor kids or if there's more poor kids? That's the question. What? I know that's like not proper, but I'm trying to like put some English back into this, right?
It sucks regardless.
It does suck regardless. But what we just learned is that it sucks more in some schools than others.
Right.
Right? So that's what I want to know is why. What is that suckiness related to? Yeah, let's see. So I'm putting in this as a cross-level interaction between the 2 pieces of the variable. We have it right there and right here. Here's my solution. This gets a little bit tricky, but we can handle it. I know that we can. Intercept here, has it changed interpretation difference? Might be a little bit different number, but it means the same thing, because we haven't introduced any new variables into the story. This is still a kid who pays for lunch and goes to a school where 70% of the kids pay and 30% get some kind of discount. Okay. This fixed slope right here is my within school effect. Kids who get a discount do worse on average by 8.67. Is that the end of my sentence?
No.
It is not. I'm not normally one of those people who end sentences in a question. So if I do that, that means I'm not done talking. Uptalk, I think, is that what it's called? There's a term for it. It's a thing. I have to take into account the fact that it's part of that interaction. So minus 8.67 is the gap specifically when the interacting predictor is 0, which is specifically for a school where the split is 70-30. In that school, the disadvantage is minus 0.867. The interaction term, remember the rules? Let me zoom in here. There's 4 kinds. Interaction terms take their main effects and make them more positive, less positive, more negative, or less negative, which is this.
Less negative.
Yeah, less negative. So is it making the effect stronger or weaker?
Weaker.
Weaker as the interacting variable goes up. So we have the same weirdness with respect to what a unit is. For every additional unit of cluster mean lunch, the disadvantage is reduced, is less negative by 3.9. Or if I want to talk about it per 10%, the disadvantage is reduced by 0.39 instead. And that happens to be non-significant. You could also interpret the interaction the other way, but I find that one a little bit harder to think about. So we'll just do it one way for now. Yes. So I'm starting with lunch disadvantage at the student level as the focal predictor and school composition as the moderator. So in a school where the composition split is 70-30, the student level disadvantage is minus 8.67. For every unit more of the composition moderator, that disadvantage of minus 8 is reduced, less negative, by 3.9. Given that a unit in this variable is all the range it could possibly have because it's a proportion, I can change this by moving the decimal over again and say for every 10% more poor kids in your school, the disadvantage is less negative by 0.39. And yes, your readers will hate you if all you say is less negative. Nobody handles that well. So you got to invent more words. The disadvantage is reduced. That's what less negative means. Pick your favorite term, but less negative is not going to fly. There. Okay, now which variance should this cross-level interaction have reduced? You've got 3 choices.
Random slope variance.
Yeah, it should have reduced the variance that goes with that predictor. Yes.
There is something weird in those results when I try to understand this example, because we can see that the contextual effect is negative. So we are saying that keeping individual or student characteristics constant, if we move that student to a new school, we know that the difference would be hypothetically minus 18, right? However, when we try to understand that interaction, that is the difference between students who pay with respect to those who don't pay,
Mhm.
but depending on the school composition, right?
Mhm.
But now the effect is positive.
The interaction is positive.
Yes. So the expected difference would be reduced based on the interaction.
Yes.
However, based on the contextual effect, that gap should be increased, right?
No, the contextual effect is in the same direction. So if we go the other way, this main effect right here is now specifically for zero value of the interacting predictors. So this is the composition effect in kids who pay. And in kids who get a discount, it's less negative by
Oh, yeah.
3.
Yes,
So it's actually
yes.
the same pattern of like, there's bigger differences among the kids that pay.
Yeah, because that's
if you go that
conditional
way.
too.
Yep,
Yeah,
they're
you're
both
right.
conditional on each other.
You're right, thank you.
So we said that this new interaction should have explained the random slope variance, right? Let's see how much it did. 6%. So 6% of the reasons for differences in the free lunch discrepancy have to do with school composition. Residual variance didn't change much. Random intercept variance actually went up. So let me ask you, is this model okay? Or did I break a rule? Oh, yeah, shit, she did. What did I do? What did I do? That's right. The rule is whatever you do to a level 1 predictor, if it's constant centered, you got to do the same thing to the level 2 predictor. So what I did to my predictor is interact it with this variable. So how do I fix it? I need to interact the level 2 part with this variable. They're the same. That doesn't change the rule, though. So yeah, this cross-level interaction is smushed. This 3.9 is saying that the within-school effect of free lunch is moderated to the same extent as the between-school effect is. Same principle, just at a higher level of complexity. To fix it, whatever I did to the level 1, I have to do to the level 2. That's going to create... Now I got to zoom back out because my model's too damn big. This one right here. And yes, I do tend to use sort of long variable names in my equations because they're easier to read. But you can shorten it as ever you'd like. So yeah, we need to add the corresponding level 2 interaction to unsmush the cross-level interaction. And then I have reminders here as to how we get model implied slopes with respect to the between effect and the between level interaction if you're interested in that. So here's my new quadratic effect. In R, it looks a little bit different. It won't let me just make the terms as a regular interaction, so I had to do it that way. And R, of course, reorders things against my will. So the cross-level interaction before was this 3.9, and it wasn't significant. The cross-level interaction now is 5.3, and it's closer to significance. It's heading in the right direction. It's trending. That's because we have pulled out the between confounding out of this. So our new level 2 interaction, you could think of it as a contextual interaction. It ensures that the cross-level interaction is referring to moderation of the within-school effect specifically, not the smushed version. Okay, so maybe I was optimistic that we're going to be finishing this today. Looks like I'm prepped for Thursday. Woo!
That's great. That is good when that happens, though.
Isn't
It's
it?
like, all right,
Yeah, tomorrow just got a whole lot better.
naturalistic learning.
Yeah, it's hard to say whether I'm doing this for the benefit of greater understanding or the benefit of me getting sleep tomorrow night. You know, like either, like it's the same goal. I love it when a plan comes together. But no, this shit is really hard, so we will spend as much time as we need. That's my plan. Now, what to do with all this stuff here? Okay. So 5.37 is how the within-school effect differs by school composition. It's the same interpretation that we were trying to give this one before, but this wasn't the right number. So it's actually a little bit bigger. The disadvantage is reduced in schools that have more poor kids. That's how I would say that. Maybe not poor kids, that's probably not like a nice thing to write down, but come up with whatever term is better than that. Now, what to do with this one? That's a little trickier. Guess how many kinds of quadratics there are? Quadratic slopes. Would you like to guess? No, you're not feeling it?
This is not a finger question anymore, because it's that many.
No. How many kinds of interactions did we say there were? 4. A quadratic slope is an interaction of a predictor with itself. So I'll repeat the question. How many quadratic slopes can there be? There's 4 kinds of those. It's the same 4. It's the exact same concept. The main effect slope is negative. The interaction slope is negative, so which kind is this? The interaction is making your main effect more positive, less positive, more negative, or less negative?
More negative.
More negative, yep. So it's creating a line that accelerates as you move down, like off a cliff. That's what it's moving. So the effect of the variable becomes stronger as you move higher into that variable. And several of you have learned the quadratic rule. If I want to talk about this slope as how it's adjusting the main effect, what do I have to do to it first?
Multiply by 2.
Multiply by 2. That's the rule. The reasons for that, you can either explain it in terms of calculus, because we're talking about the second derivative of the function. And when you differentiate, the 2 that was in the squared term comes down in front. If you don't like calculus, most of us don't, then you can think of this in terms of the rules of interactions. If I normally have an interaction between 2 variables, like x and z, we'll say, the interaction term takes the effect of x and changes it as a function of z. It simultaneously takes the effect of z and changes it as a function of x. Here, I only have one x. I don't have the corresponding z part. It's the same variable. So whatever it was going to do twice, because it had to do it to 2 different variables, it has to do it twice to this one. That's the way I think of it. I have no idea if that makes sense mathematically, but it makes sense to me, and it helps me remember. So putting it all together, this is the slope of this variable, conditional on its interacting predictor being 0, which is itself. So this is the slope of this variable at 0.3 specifically, which is when it is 0. That slope becomes more negative by 22 for every unit up in the variable. But the unit, again, is the whole thing. So 1.1 per 10%. And yes, I do have some pictures. Because at this point, your readers are going to be like, oh my God, I have no idea what she's saying. And we'll have to get a picture out. The new one is not significant. The cross-level interaction is close. Go ahead.
Quick question. So if we wanted to do increments of like the 10% again, which one changes of the cluster mean school composition?
I would change both of them if you're going to do that, because they're the same variable, and I think it would be weird to change one and not the other. So, like, if I wanted to change this, this would be at 0.3 specifically. There are, for every 10% more kids, math goes down by 1.8. And then as you move up the variable, the slope becomes more negative by 1.1 every 10%. So let me get paint out for a second here. This one? Okay, let me get a negative slope. So a negative linear slope would be this, right? Constant. The one that we've created is going to be like that. So the main effect is specifically when the predictor variable is 0. So if it's at 0.3, let's say that 0 is right here. Then the main effect is this slope, to the best of my drawing ability. This is the line that's tangent to the curve at that point. So if you follow your slope like down the hill, it's getting steeper. So the main effect is whenever your centered predictor is at 0, and then the interaction with the quadratic that it's creating takes it down the hill. I don't know if that helps, but that's how I think of it. So more positive looks like this. Less positive looks like that. More negative is this one, and less negative would be that one. There's only 4 kinds. Altogether, a quadratic is either this or this. It just depends on where you start in terms of where 0 is, like what side you would see. And I'm going to make this guy happy. There. Because we don't want to end on a sad note, do we? No unhappiness right here, just happy use.
We're happy that class is ended.
Exactly, aren't we? I'm happy that I'm prepped for Thursday, because we're not done yet. You remember at the whole beginning of this example, what I said was still coming? I got a whole nother variable. Because right now my model is saying that there's no difference between the kids who get a discount or they qualify for free. That's an empirical question. So stay tuned for the exciting conclusion of how free lunch predicts math scores. 140. I think that's a good place to end. So, things you want me to say again or questions before we call it a day? Good? Good enough, at least? Yeah, good enough is that's all we're going for right now. All right, thanks for being here then. Let me know if you need anything. And I'll see you Thursday. Woot. Bye, Zoomers.